Assalamu alaikum. In continuation of our previous class, where we presented double sideband modulation, double sideband suppressed carrier, we actually shown that how the demodulation actually is done, right? So in demodulation, so what we say that demodulation of the double sideband suppressed carrier is done by a coherently generated carrier. Okay, so we will actually continue with this one, this lecture, where we will actually again draw the schematic diagram. So let us write what is the received the modulated signal xt. The modulated signal xt equal to ACMT cos 2 pi fct. Now, what happens? This signal mt cos 2 pi mct, this signal actually, when it is received, it is actually mixed with a carrier signal, which is actually cos 2 pi fct, and the combined signal, you see here, when we demodulate this signal, the received signal, we say the received signal actually state that the received signal is coherently generated. It will be multiplied by the coherently generated carrier signal. This signal, it will be multiplied by the, so which will be done in a mixture, RF mixture. So the signal then pass through a low pass filter, and we got the output signal. So the bandwidth of this low pass filter is nothing but like this, minus W2, W. We have seen it here, minus W2, W. And we have seen that this is the condition. This condition should be fulfilled. This condition should be fulfilled for, means the cutoff frequency of the low pass filter should be much higher than the frequency of the message signal, but it should be lower than the sidebands, like lower than the sidebands. Okay, so cutoff frequency fc of the filter, pass filter, this one. So fc cutoff filter should be greater than the fm, but it should be the twice fm, twice fc carrier. Okay, now this is the condition. So this is the condition. This is actually the schematic of the DSB. So this is actually a schematic diagram. So this is the schematic diagram of a double sideband suppressed carrier demodulation process. Okay, demodulation. So this is the double sideband suppressed carrier demodulation process. Here, a amazing things happens is that when the signal is received here, you see, when the signal is received here, this is actually at the receiver side. Yeah, this is happens at the receiver. Means actually this is received by, for example, an antenna signal, whatever. So when you receive the signal, we can generate this carrier by a local oscillator, LO. This is locally generated carrier. This is locally generated. So this is locally generated. So this carrier is generated locally. What does it mean locally? Means when you receive the signal, you generate this locally generated carrier, where the phases, you see there is no phase here. Means you know in advance that there is no phase in the received signal also. Means actually the phases are equal. So what we can say, the phases are phases are equal. So we can say the phases are phases of what? Phases of the received signal and the locally generated carrier, the phases are equal. If this is the case, then we call this demodulation is a coherent. This is a coherent demodulation. That's why actually this word was previously used. Coherent. This word was coherently generated carrier. This carrier was generated coherently. Coherent means like something synchronized. It follows. Means the local oscillator should have the knowledge of the phase. They have this equal phase. Okay. Okay. So this is actually coherent detection. So this mechanism is actually a coherent demodulation. Demodulation. Why it becomes coherent demodulation? Because the knowledge of the phase, the phases of this receive signal and the phases of the local oscillator, they are same. But the problem arises that it is not always known. That is the means that there is no phase offset between these two. There is no phase difference between these two. So this is called coherent demodulation. Now, problem is that these phases is not always known. It can happen that there is a phase, there is a phase in the local oscillator. Means, for example, how the local oscillator knows what is the phases in the received signal. There is a synchronization between the transmitter and the, this is actually received signal coming from the transmitter, right? This signal. So there is a synchronization between the transmitter and the receiver. If the receiver and the transmitter and the receiver are not in synchronized, then means there is a phase offset. Means in that case, the signal xt. Okay, so in that case, it is a non-coherent demodulation, right? So if there is a phase offset, there is a phase offset, means there is a phase difference, then that is called a non-coherent demodulation. So this is a non-coherent demodulation if there is a offset of the phases. So let's see. So in general, so if we have a signal xt is a cmt cos 2 pi fct, right? This is our received signal. Now this is our incoming signal or received signal. It will be modulated by who? It will be modulated by the cos. Previously in coherent demodulation, cos was by fct. This was the signal or carrier signal. Now a new phase is introduced here. Okay, so this is the locally generated carrier, but they are non-coherent. Okay, this is also a locally generated carrier, but they're not incoherent. Means this carrier or local oscillator who generate this locally carrier local carrier do not have a knowledge of the phase. Okay. Okay. So we can say this is actually a carrier phase offset. Carrier phase offset. If the carrier phase offset becomes 0, then carrier at the receiver or the local oscillator is coherent, and if not, that is non-coherent with respect to the incoming signal. Okay, means if if carrier, if the carrier phase offset, which is actually this is not equal to 0, if this is the case, then carrier at the receiver or local oscillator is not coherent. So what we can write that carrier at receiver or local oscillator is not coherent with respect to carrier of incoming signal or incoming signal or receive signal. Okay, so if there is any phase, then this is called non-coherent demodulation. Okay, so xt, this is our xt signal, which is previously used to multiply with the cos 2 pi fct. There was no phase. Now we introduce a phase here. So if we rewrite the, okay, this is signal rt, this is signal rt. So AC, we know xt equal to AC mt cos 2 pi fct. Here at the transmitted signal which was received, there is no phase introduced, right? This phase actually was introduced in the local oscillator. So cos 2 pi fct plus this phase. Okay, so we can write it. Equal to actually AC mt. This cos term is together. Okay, so this cos term actually, if we together it, so cos A cos B, actually 2 cos A cos B. So if we write 2, then make it half. So 2 cos A cos B becomes cos A plus cos B. Okay, actually it is actually cos like A plus B. So A, so which will become 2 pi fct, 2 pi fct becomes 4 pi fct plus theta, 2 cos cos A plus B plus cos A minus B. So cos this one minus this one. So this term will be this term will be crossed. So it's actually nothing but cos this angle, cos phi, or cos cos phi. Let's say call it cos phi. Okay. So if I take it out, so half of AC mt cos phi, this term I take it out, plus half AC mt cos 4 pi fct plus phi. So this term, we have actually two terms. This term is a baseband. This is actually the baseband, and this term is actually because of the sidebands. Sidebands actually there for the sideband. Okay. So here you can see this additional phi was absent previously in a coherent demodulation. Okay. Okay. Now, okay, we can find the power of the demodulated signal. Okay. So, power of the demodulated signal, what we can write from this. So, power of the demodulated signal the demodulated signal. So what is the power of the demodulated signal? Because of this, what the power becomes is nothing but 1 by, remember how we find the previous power? A square. Actually, power is nothing but the square of this one. It will be like square of the whole term, base term. So it becomes 1 by 2 becomes 1 by 4 a square. M square T, it was our power. We actually give it a name previously, PM. And cos theta becomes cos square theta. So cos square, actually phi, cos square phi. That's when the phase is included. Okay. So power of the demodulated signal. Here actually this is the baseband signal. That's why actually this is the baseband signal. So we are considering what is the power of the demodulated signal, which is this one is lower of 1 by 4 s square PM. Okay. So here what we write, this is cos square phi. What is the maximum value of cos? So you see here, the previously this was actually our baseband power, the receive signal power, the power of the demodulated signal. Now this is actually power of the receive. We can see this power, this decreases by a factor of this term. So we can write that output power decreases by a factor of cos square phi. Okay. So cos square phi. Yeah. What is the for cos phi equal to pi by 2? What is the maximum value? Pi by 2, it becomes 0. Yeah. Yeah. So the output power decreases by a factor of cos square theta, which is actually should be less than or equal to 1. Because in fact, because for pi equal to pi by 2, cos 90 degree is 0. Cos square by this becomes 0 for pi by 2. This is actually nothing but 90 degree. If locally generated carrier is orthogonal to the carrier wave in a incoming signal, this happens that if okay, this is actually the not the multiplication. We write it if pi equal to pi by 2 means 90 degree, cos square becomes 0, which actually implies that locally generated carrier is orthogonal to the incoming carrier of the incoming signal. Okay. So the so here we just see if and the cos the phi becomes pi by 2, means if it's 90 degree, that this whole terms become 0, which actually ultimately will make this baseband power also 0, which actually implies that the locally generated carrier is orthogonal to the carrier in the incoming signal. Means if when the signal is coming, you are multiplying with this carrier signal or local carrier signal. If this signal is 90 degree phase shifted from this received signal, then you actually will get nothing. Means the demodulated signal will be 0. That's actually it's saying the orthogonal of the incoming signal. Means if this angle becomes, so what is orthogonal? If a signal or two signal is apart by pi by 2, then signal x and signal y, they are called orthogonal. So we can also see that the received signal and the modulated signal, when their phase difference is pi by 2 to pi by 2, which is actually, which makes this cos square phi equal to 0, which ultimately will make the whole baseband signal 0. Means the signal received here will actually, the signal power received here will also be 0. Means actually the as phi increases, so we can write that as phi increases, output power of the demodulated signal decreases. So if as the phase difference between the two signal, the signal is received or signal we generated as if their phase difference increases, the demodulated signal will keep decreasing and it will be 0 at this degree, at 90 degree. Means if when the signals are orthogonal to each other. So to maintain this phase phi is very important, and it should be as low as possible. So if it's totally 0, no phase difference, then we get the maximum receive power, which actually happens in the coherent demodulation. If it's not, then it's a non-coherent demodulation, which actually gives a lower or decreased received signal here at the receiver. At the demodulated signal will be low power. So it is very important to maintain this coherency. So this is the end of the non-coherent demodulation. Assalamu alaikum.